So in this lesson we're going to concentrate on generators and what is special about generators. What makes them generators? What is your input? What is your output? Your input is mechanical energy. Mechanical energy. And your output, you wrote this down last week. Your output is electricity. Yes, electric current. Okay. Now the construction of the generator is very similar to the construction of a motor. Where you'll see the difference is that in the circuit of a generator you won't have a battery. In the circuit of a motor you'll have a battery or an AC power supply. Where in a circuit of a generator you'll have a load. So you'll have a load as in the external circuit. Where you had a battery or a AC power supply in the external circuit of a motor. Are you fine? Okay, so generators have what they call an axle, or motors as well. But this thing turns mechanically, it is mechanically turned. Now the construction of the AC generator, it looks like the AC motor. What did we have in an AC motor? A split ring. Are you sure?
A slip ring.
A slip ring. Check quickly.
It's a slip ring.
It slip rings in the AC motor. In the AC motor. So what will you have in an AC generator? Slip rings. So in the generator, there's no current yet. That's why I'm drawing the green circles for the conductors as empty. And this is the slip ring that is connected to the green part of the coil, and the slip ring that is connected to the yellow part of the coil. So there you have brushes making contact with the external circuit. Now, we need to use mechanical energy that will be converted into electrical energy. So first, we need to decide in which direction are we going to turn this thing. Are we wanting to turn it clockwise or anti-clockwise? You decide. That helps us too. You want it to turn clockwise. So mechanically it's going to turn clockwise. So the loop is turned clockwise. Yes.
Who's turning the loop?
Who? You.
Okay, but in the motor, who was turning the loop?
Steam or water
So does it matter in which
or
direction?
wind.
Does it matter which direction?
Well, we need to know the direction so that we can see in which direction the current will be induced.
So doesn't magnetic field go from north to south?
The magnetic field goes from north to south, yes. The magnetic field here is going, so the magnetic field is in that direction. That's the magnetic field's direction,
So that
from
doesn't-
north to south.
That doesn't affect in which direction the loop is turning.
No. But it will affect the direction in which the current is going to flow. Okay. So in the vertical position, no current will flow because the motion is parallel to the magnetic field. If the motion is parallel to the magnetic field, there's no change in magnetic flux, so no current will be induced there. You understand? Okay. Now, you're turning the loop. So this green part is going to move this way. Okay. As it moves this way, as it moves that way, it's going to be on this side. And it's moving how? Down. Okay? So the direction of the force on this loop is down. And that one, the yellow one, is going to move up there. You'll have to follow the video to see what is happening. So this thing is turning clockwise. Now this part is now there, and this part is there. What is the direction of the force? What is the force on the loop, on this part of the loop? It's up. Now we need to use Fleming's right-hand dynamo rule to see in which direction the current is going to flow as the coil or the loop turns in the magnetic field. So we don't know the current now. We don't know the current. We know that this part is moving up, so our thumb must point up, and the magnetic field is from left to right. So in the yellow part, the current is flowing away from you. Now I can put a cross there. Am I right? I can put a cross there because in the yellow part, while the yellow part is moving upwards in this magnetic field, a current is induced. Yes.
So for a generator, we use the right hand. And for a
Yes.
motor, we use the left.
Yes. Okay. So, because the generator is just the opposite to the motor, you use the motor rule is the left-hand rule, and the generator's rule is the right-hand rule. The fingers intend the same meaning, but now it's opposite. So, you see, the one is a mirror image of the other one. So, through the green parts, the current is coming towards you. All right? Through the green part, the current is coming out towards you. What color shall we choose? Nice orange. So here, the current is coming out, so it runs through the slip ring and it runs through the circuit in that direction. The current is now the orange part. Shall I use a thicker one? So it comes there, in, out the coil, out here, in there, and it flows in this direction. This is the direction of the current. Okay. What's happening to the size of the current as this thing turns from the vertical position to the horizontal position? What's happening to the size of the current? It increases. Okay. What happens to the size of the current when it turns further back to the vertical position? It decreases. Are you with me? Okay. Because as you turn it, the surface, the magnetic flux through the coil is getting less. Say this hand is the coil. If the hand is in this position and my right hand's fingers are the magnetic field lines, then that change in magnetic flux is small. But if it turns, the change in magnetic flux is bigger. So it gets to a maximum. And then if it carries on turning, the magnetic flux is getting smaller again. So the induced current will flow like this, if I can show you. If I draw, remember it's now an induced current, and rotation graph. If we start in the vertical position, the current is 0. And the current increases as the coil turns through how many degrees? 90 degrees. And then when the current turns further, when the coil turns further, the changing magnetic flux gets weaker, less and less and less, so the induced current gets less. So when we get to the 180 degree turn, the current will be zero again. So it's from vertical position to horizontal, from vertical position to horizontal position is increasing current, from horizontal position to vertical position is decreasing current. Okay, so at the moment my graph is representing this situation. Which one was at the top? The green one. Yes. So now, in this place, when it goes into the vertical position, again, then there's no current flowing.
Which would be after 180 degrees.
That's after 180 degrees. But remember, somebody on the outside, whether it's steam coming from a turbine, wind blowing the blades, turning the blades and turning the turbine, or water falling through the turbine, turning the coil in the magnetic field. It's an outside force, it's a mechanical force, is turning this thing. So what will happen when this part of the loop is there and that part of the loop is there? The current will now increase, yes, but in which direction will it flow through the loop?
In the opposite direction.
So what you're telling me is that it will flow away from you now in the green part. Yeah? And it is flowing towards you in the yellow part. Now look at what happens here now. Let me just take away all these arrows. Okay. So now the current is going into the coil from this side, and it flows away from you. And it comes out through the yellow part. So it comes out there. Can you see that the direction of the current has changed in this half of the cycle through the external circuit?
I get everything, but the thing is I don't get when the loop turns, right? And then the green part was the side, now it's going this side. How does it change its current? Like I get into
It's the motion.
In the graph, I get it.
Yeah.
Like in the drawing, I don't get it.
Okay, I'll use that model again just now. So here, this part of the loop is now moving up. This part of the loop is moving up, and that part of the loop is moving down. So let us see, using the right-hand dynamo rule, in which part, in how the current will flow. So here the current is flowing away from you. The force on the conductor is up. Okay? The reason why the current is flowing away from you is the force is up and the magnetic field is from left to right. That's how I see in which direction the current is flowing. Did I answer your question?
Yes, ma'am.
Okay. It's a bit more difficult here because here you have to do this with your hand and that's very difficult. It's awkward. So go to that.
On like it depends on how they turn. For example,
Yes.
if they here, we know you can determine by using our hand.
Yes.
Okay.
Yes.
Ma'am.
Yes.
So the loop is always going to turn in one direction.
Yes, because you're turning it from the other side, from the outside. You are using mechanical energy to create electricity. But the electricity created with every 180 degrees, the electricity will flow in the opposite direction. So our graph becomes after reaching the vertical position again, it now turns to the horizontal position, but in the opposite direction. The current is flowing now in the opposite direction. And as you continue turning it, so after 270 degrees, you're at maximum current, and this part will be in the vertical, that will be going through the horizontal position there. Your current, your loop will be in the horizontal position there, with the current being, the induced current being the biggest when the loop goes through the horizontal position. So after the horizontal position, the current now decreases again as it goes back into the vertical position. So 360 degree turn, rotation of that loop will give you this kind of graph. Any questions? Yeah. Just to go a little bit smaller, slower. Do you still want to turn clockwise? Okay. So while it's turning clockwise, from the vertical position, the current is 0. So that is our rotation. This is the current. So we start off with the current being 0. What happens as this thing turns through from the vertical position, it turns in that direction. What's the direction of the force on the conductor? Down there and up there. So in which direction will the current flow? For the green one or for the yellow one? Because if you've got the yellow one, you will sort out the green one. The yellow one will create a current that flows away from you, and obviously then the green one will have a current that flows out towards you. So let's look at how the current will flow in the external circuit. It will come out from the coil to the slip ring, and it will flow in this direction. Am I right? I'm using the yellow and the arrows now. The current will flow in this direction. That current is now a maximum when the loop gets to the yellow to this position. It is now a maximum. What do you call a graph like this in mathematics? Sine graph. Yes. So there we have our maximum current after a 90-degree turn. Now we continue turning the loop in that direction until it reaches the horizontal position. What will the current then be? It will go down to 0 again. Okay, so after 180 degrees, the current in the loop will go back to 0. Okay, because there's no change in magnetic flux when the loop moves through that position. Now, as it goes past that position, you carry on turning it in that direction. So our force here is still down, force there is up. Okay, in which direction does it go through the green part of the loop? Now it's going away from you, and through the yellow part of the loop it will come out towards you. So if I follow that, look, the yellow part is linked to the yellow slip ring. The current will come out from the loop through the yellow slip ring, and now the current is flowing in the opposite direction through the external circuit. and when it reaches the horizontal place, then the current will be at a maximum. Is it all right? Is it clear now?
Yes.
So after 270 degrees, you'll reach a maximum current again, but it will flow in that half of the cycle. It will flow in the opposite direction through the load circuit.
Ma'am, what happened to color is go to the developments of the stages of the rotation of the loop, the drawings of the go to the second last drawing.
This
Yes,
one.
yes, ma'am. What happened to is it no current flowing?
No current flows when the loop is in the vertical position.
Okay, the first drawing is when the loop is at 0 degrees.
Vertical position, yes. From the vertical position.
And then the second one is 90 degrees.
90 degrees turn, then it's in the horizontal position, and that's where the maximum current will be flowing through your circuit.
Ma'am, you said maximum current flow through is like in this drawing is like a space.
Yeah, where the change in space is the biggest.
So then how does it? Okay, you see the vertical. How does the vertical look on that?
Okay, when the coil is in the vertical position, there is quite a lot of magnetic flux, but the change in magnetic flux is small. So your magnetic flux here is this. There is a lot of magnetic field lines going through, but because the loop is in the vertical position, the change in flux is very small.
Oh, so
It's about, you see, this is now the problem why your understanding lacks, because we didn't do those calculations. But as the loop turns through into the horizontal position, the change in flux increases, the change in the flux increases.
So then it's not about the flux, it's about the change.
Yes. So here, there's no flux through the loop. So it changed from a maximum flux to a zero flux. And that's the biggest change in flux. That's why the current will increase. And now, as you change back into the vertical position from the horizontal position, there will be an increase in the change in, no man, I'm talking nonsense again. There will be a smaller and smaller and smaller getting change. The magnetic flux is changing smaller and smaller and smaller, so the current will decrease again.
Now, okay, you see the drawing, okay, so the stages of rotation of the loop, and also with the graph. You see the last stage that yes, ma'am, is that where the 270 is, where the maximum is, and also
Current again.
the reason why it's going back to the graph, the reason why it's opposite is because it's in opposite direction.
Yeah, the current is
And the
going
current is
in the opposite direction. Look at the arrows changing from the second place there. The current was flowing anti-clockwise through the loop, and now it's flowing clockwise through the loop.
So now
Yeah.
the y-axis of this graph would be the current.
Yes, sorry, could be current. It could also be voltage. So you'll see in your textbooks, sometimes they use it as EMF, sometimes they use it as current. Faraday said the induced EMF is directly proportional to the rate of change in magnetic flux. So Faraday referred to the EMF. If I can draw this, it will look very messy, but I will draw it just now. If we look at your EMF, I'm going to draw it on the same graph here. Your voltage will be a bigger value than your current value. The induced voltage is bigger. So the two graphs are in tandem, if I can say it that. They're stepping the same at the same pace, but the numerical values for voltage and for current won't be the same.
The amplitude is higher.
The amplitude for the voltage is higher. Yes. Did I answer all your questions? Are you okay with this now? Okay. What if the loop starts turning from the horizontal position? Now you have given it thought. Let's just talk about it. So if you have your current or your voltage and time graph, what will it look like then? Or rotation, not necessarily time. They can have time. Let's do time. So what do you want this to be? Current. Okay, so current, this is our current graph, and this time the loop starts turning from the horizontal position, so your current will be a maximum. So the current will decrease as it turns into the vertical position to a 0, and then it will increase to a maximum in the opposite direction, and it will decrease again as it turns back to its vertical position and increase. How many rotations have I got here?
1, 2, 3. One rotation.
This is half a rotation. This is half a rotation. That's half of a rotation. And this is another half of a rotation. Half of a half a rotation. And that. So I've got a turn through 90 degrees there. A turn through 180 degrees there. A turn through 270 degrees there. And this brings me to one cycle, 360 degrees. Now, I've referred to degrees, but can you remember about period? Period.
1 over frequency.
Yes, period. T is 1 over frequency. So, what is the period here?
It's 1. It takes 360
This is
degrees to
one
complete one cycle.
period. What is this part of a period? A half a period. And this would be a quarter of a period. What is a period in South Africa? Come, what's the value of a period for our AC current?
Isn't the 0.1
Come, what's the frequency?
the 60 in South Africa? 60
Eyeball.
is under 50.
AC is,
50.
the frequency is 50 hertz.
0.02.
So what is the period here? 0.02 seconds. So they could ask you or refer to the degrees of rotation, or they could refer to cycles, or they could refer to period.
So this represents a period.
One cycle. This represents one cycle, which can be represented by a period. All right.
And 1 period is 0.02 seconds.
For our alternating current generated, alternating current. You can obviously get generators that turns faster. So it's not something to break your mind over, but you need to be aware that you can look for things like this. Okay. So we've replaced the current, the cos graph with a sine graph again, because I feel it's going to be easier to show what happens using the sine graph. So I want to superimpose the EMF graph onto the current graph. And then I want to show you something beautiful. Absolutely beautiful. So the EMF graph would be reaching a higher peak than the current graph. You've got that already. Nothing to worry about. That's what it will look like. Now, I made a statement here that it's all about power. Yes.
Is it because, okay, this is EMF, is it because it needs to overpower the current to push it?
You need more energy to push the charges. Yes, yes. That thing, if you want to visualize it like that, it's true. The current that can come out these plugs are 30 amps, but the voltage is 240.
Yeah, no, I wanted to say, isn't it only like
20 amps.
Isn't it like 50, you know, because 30 is...
Okay, in our house it's 20 amps. Yeah.
Around.
But because we have three-phase, it's much higher. Okay. What about power? Come on. Tell me about power and its relationship between voltage and current.
It's directly proportional if the one is...
So what is the equation? P equals V times I. Now I'm going to have to rely on your mathematical ability. Naught times naught is naught. A maximum current times a maximum positive current times a maximum positive EMF will be a... Yes. So look now, it's playing with mathematics. This part is naught, but that part will increase like that. So I'm now superimposing the power graph onto the EMF and the current curves. Can you see what's happening?
Yes,
Alright. Now, naught times naught is naught, naught times naught is naught. What is minus current times minus voltage going to be? Yes. So the power graph that is married to this EMF and current curves is this. Your power output, can you see that it varies a little bit, but it's always positive? Alright? Okay. That is beautiful mathematics. Come on. Now the thing is here, there was a question about what happens when the power drops to zero. The thing is, the power drops to zero in a split second, and in a cycle it can be zero like 3 times in 0,02 seconds. So the effect of the power of an alternating current dropping to zero is negligible. But the power has a maximum output. When does the maximum output take place? Also, in a split second in a cycle, in a very small time. So, can you see that your appliances that you connect to the source of electricity won't be rated according to the maximum power output of the generator? Because the maximum power output is only for like twice in a cycle, for that moment when the coil goes through the horizontal turn position. So we work on average power. The average power output is the effective power output. All right? Yes? So, how do I get, if I've got a maximum power, how do I get average power? How can I get average power if I've got a value for maximum power? How do you get averages in mathematics? You divide it by 2. Okay? So please bear with me now because I'm trying to bring you into the maths behind it. So average power is maximum power divided by 2. Alright? How can I get maximum power? How can I get this maximum power?
2 times the average.
No, wait now. V max times I max. Are you with me? The maximum power there is the V max there. Should make it a black dot there. That V max times I max. Okay. You got me? You're moving with me. Alright. Now, V max times I max will give me P max. So what must I do with this V max times I max to get the average power? I must divide it by 2. Divide it by 2. Wait for it, it's coming your way. If I want to separate this 2 to write it as V max divided by something times I max divided by something, what is the mathematics behind something times something being equal to 2? What is x times x, which will be 2? Is x squared must be 2. What will the x be?
Plus or minus 2.
Wait a moment.
Square root.
Okay, here we don't work with minuses. Although mathematically it should be plus or minus the root of 2. That's the correct maths. But here we don't work with negative powers. So if I want to split the 2 up into, it will be the root of 2 times the root of 2 will give you 2. Are you with me in the mathematics there? So this V max divided by the root of 2 times I max divided by the root of 2 will give me the average power output of your generator. Alright?
Isn't it just V max over 2 times I max over 2?
What is 2 times 2? That's not, the 2 isn't 4. 2 is not 4. You see, I've tried to work from what we can measure, the power maximum, and how we can convert it to average power, because the average power will be the effective power. And you just divide it by half, or you multiply it by half, divide it into 2 parts, then you'll get the average. But how do you calculate your P max? Your P max is V max times I max, divided by 2 to get the average power. Now, I want to work towards something. It's the effective voltage of your generator and the effective current of your generator. Listen carefully. It's called the root mean square voltage. root mean means average squared. So this is VRMS, root mean square voltage, times IRMS. So it is somewhere here. That mean, that average voltage and the average current, the root mean square current, those two multiplied will give you the average power. So there you have it. Root mean square. The root comes from the root, mean comes from 2, meaning average, and square, root mean square. So what is VRMS? It is Vmax divided by root of 2. What is Vmax? It is root of 2 times VRMS. What is IRMS? IRMS is Imax over the root of 2. And what is Imax? Square root 2 times IRMS. Before, I want to do the DC generator first, before I want to go into the definition of VRMS and IRMS, because we've derived the equations for it now, but we haven't really defined it. There's no sense in defining it before we have done the DC generator. But there is a key here to the calculations. The power ratings on appliances refers to the average power, not the maximum power. Okay? So the effective power is the average power, which is the rating that you'll find on your kettle, your toaster, your heater, things like that. Yes.
And on the day makers find there's the maximum power.
They can. They can.
You just tell them that
By root 2.
No, you'll have to take the maximum voltage and the maximum current. Oh, I understand what you're saying. Yes, could be possible. Yeah. So the average power is referring, that rating refers to average power, and the voltage given with the power will refer to your VRMS. Okay. That's just the key to that. Okay. So an example of a problem. They've got a hairdryer and it is marked 1500 watts and 230 volts. So that would be the rating of the hairdryer. Yeah. So the first part of the question asks for the maximum voltage.
It's going to be the V max.
Yes. So it is important because often people think that the rating gives you the maximum voltage. But the rating gives you the VRMS and the P average. Okay? So the maximum voltage, Vmax. Please, they are very mean here. Very mean. You have to get the subscripts right. Don't leave the subscripts out. So when you're working with alternating current generators, you have to. You can't just use P equals VI. You've got to use the correct one. It's P average is VRMS times IRMS. So these things, RMS is important. Okay, so what's Vmax? So it's the root of 2 times VRMS. So root of 2 times 230, and you said 300 and?
325.27.
And the unit is the volt. The B part of the question asks for the resistance of the hairdryer. Right, I'm going to wait until you've thought through it a little bit, and then we can look at how to answer it. So we have a suggestion here that we use P average and V squared. Is it the V squared is the V RMS or the V max that we use here?
RMS.
The V RMS over R. I think that's a good idea. 1,500 equals 230 squared divided by R. What is the value of R? 35.27, and the unit is ohm. There was another idea. Can we use the maximum value? Then you have to first calculate the maximum value. But once you've got the Vmax, can I go that way just to show you? What about the maximum power? Path. Okay, so once we've got P average, we can use that to get I RMS. V RMS times I RMS, because depending on the nature of the question, you could be required to do this type of calculation. This question is not like that, but let's see if we get the same resistance. So your average power is 1,500, your VRMS is 230. What's the current RMS going to be? Amperes. Okay, so what is the maximum current then? Square root 2 of IRMS, and that would take us to
9.22.
9.22
Yes.
amperes. Well, can't I use Ohm's law to get the resistance here now, because I've got the voltage max and I've got the current max? Can't I use Ohm's law to say R equals V max over I max? That's my thinking now. So that would be, what is V max? 325.27, and I max is 9.22. Same answer. 35.27 ohms. So there are different possibilities. I chose to use this current story and Ohm's law rather than to use the maximum power thing. Path. Good. Can we end it here?
Yes,
Wait a moment. Oh, we did. Calculate the current through the hairdryer.
No,
It's IRMS. So technically we have calculated the current. So that was the C part of the question. The current in the hairdryer. Alright, that's enough for today. Thank you.